Today, we're diving into the fascinating world of the flower of life, a geometric figure that's steeped in history and symbolism. The flower of life is a beautiful geometric pattern that's believed to hold a wealth of ancient wisdom. It consists of multiple overlapping circles, forming a flower-like shape that's been found in various ancient cultures. In fact, it was even discovered on the ceiling of the temple at Edwin, dating back to 19 BC. What makes the flower of life so intriguing is its ability to represent the fundamental forms of space and time. This ancient symbol is said to contain sacred geometry, serving as a template for creation and depicting the blueprint for all life forms. It's thought to be an essential part of both religious and scientific knowledge. As we delve deeper into the study of this fascinating figure, we can't help but be in awe of its significance and its connection to our world. The flower of life truly seems to hold the key to understanding our universe in all its glory.
This branch of cryptography takes advantage of the principles of quantum mechanics to ensure secure communication. Let's delve into the history of its development. Quantum cryptography has its roots in the early 1970s when Stephen Wiesner, a physicist from Bell Labs, proposed the idea of quantum key distribution. He envisioned encryption using quantum entanglement and proposed a model for single-photon encryption. However, it wasn't until the late 1980s that the concept was finally realized by Charles Bennett and Gunnar Heinz-Su, who introduced practical protocols for quantum cryptography. One of the most exciting aspects of quantum cryptography is its ability to detect eavesdropping attempts with unprecedented accuracy. This is due to the no-cloning theorem in quantum mechanics, which states that certain types of information cannot be copied. As a result, intercepting information without altering it is virtually impossible in this field. So there you have it, a brief history lesson on quantum cryptography.
Kicking off our timeline is the late 19th to early 20th century, marking the early foundations of quantum theory. During this period, Max Planck introduced his hypothesis that the energy of blackbody radiation was distributed according to integer multiples of an arbitrary unit. This revolutionary concept laid the groundwork for our understanding of quantum theory. Fast forward to the year 1905, when Einstein published his groundbreaking paper on photoelectric effect in matter waves, and in 1913, Niels Bohr presented his theory of the hydrogen atom with stationary states. The years leading up to 1926 were pivotal in the development of quantum mechanics. During this time, Heisenberg developed matrix mechanics in 1925 and Schrödinger's wave equation was introduced in 1926. These discoveries allowed physicists to calculate atomic energy levels and explain spectral lines using matrix mechanics or wave equations. Finally, in 1932, Paul Dirac unified both approaches by establishing their equivalence and describing their underlying connections. And there you have it, a brief history of quantum theory timeline that covers some key milestones in its development.
Let's start with a quick recap. Quantum satellites are a significant advancement in the field of quantum communication, leveraging the principles of quantum mechanics to achieve secure long-distance communication. Fast forward to 2016, when China became the first country to successfully launch a quantum satellite named Mishus. This groundbreaking achievement demonstrated the feasibility of distributing encrypted messages over vast distances using principles of quantum mechanics. In 2018, China took another leap forward with an improved satellite called Quantastar. This satellite was designed for more practical applications, such as providing a secure connection between two cities approximately 1,200 miles apart. Interestingly, this distance is comparable to that between New York and Los Angeles. These advancements in quantum technology have paved the way for a new era of secure communication and are crucial steps towards the realization of a global quantum network. A global network like this would allow users to distribute keys or distribute encrypted messages over vast distances using principles of quantum mechanics. Did you know that the concept of quantum communications has its roots in the early 20th century when pioneers like Max Planck, Albert Einstein, and Niels Bohr laid its foundations? These scientists were at the forefront of developing the principles of quantum mechanics, which form the basis of quantum communications. Max Planck is well known for his work on black body radiation and his groundbreaking discovery that energy is quantized. This led to the theory that particles can exhibit wave-particle duality and are influenced by our active observation. Albert Einstein was another key figure in this field. He collaborated with Niels Bohr on a theory that became known as the Copenhagen interpretation. Their work was instrumental in shaping our understanding of quantum mechanics, which later paved the way for the development of quantum communications. So there you have it, a brief history of how quantum communications emerged from the early developments in quantum mechanics. It's amazing how these foundational concepts have evolved into new technologies with vast potential applications.
First up, did you know that Einstein actually coined the term entanglement when he wrote a letter to Heisenberg? That's right. In 1935, Einstein wanted to reject the idea of quantum mechanics and proposed a thought experiment involving two particles. He named this concept entanglement. Next, let's talk about Schrödinger's famous thought experiment involving a cat in a box. Interestingly, his initial idea was to use an elephant instead of a cat. However, he eventually decided that a cat was more suitable for his intended audience and the humor of the experiment. Finally, did you know that Einstein once said that if we were to use atoms as units for our measurements, we would find that the distance between New York and London is smaller than the size of an apple?
Kicking off our list, in 1900, Max Planck introduced the groundbreaking concept of quantized energy, which transformed our understanding of light forever. Another pivotal moment came in 1905 when Einstein proposed the photoelectric effect, challenging our assumptions about light once again. Fast forward to 1913, when Niels Bohr introduced his revolutionary atomic theory, laying the groundwork for our understanding of electron configurations. In 1924, Werner Heisenberg published his uncertainty principle, fundamentally changing how we view subatomic particles. And finally, in 1927, Schrödinger introduced his groundbreaking wave equation, which revolutionized the way we perceive quantum systems. Albert Einstein was born on March 14, 1879, in Ulm, in the Kingdom of Württemberg in the German Empire. His family was made up of hard-working people. His grandfather was a master tailor, while his father established Einstein's first school. Einstein himself taught there until he was 16. Einstein excelled in school, especially in math and physics. He attended Zurich Polytechnic School to study electrical engineering before switching to teaching at a high school in Bern. It was during this time that he published his groundbreaking work on the photoelectric effect and special relativity. Einstein's discoveries were revolutionary as they challenged our understanding of time and space. His work paved the way for future researchers and is still studied today. So there you have it, a brief overview of Albert Einstein's life and achievements. Let's go back to the beginning. By the 15th century, ancient civilizations had already discovered a handful of elements like gold, silver, copper, and sulfur. Fast forward to the late 18th century, and scientists had identified around 30 elements. In 1817, German chemist Johann Wolfgang de Bryner made a significant discovery. He identified something called law of triads, where certain elements had similar properties when grouped into groups of 3 with similar average atomic weights. For example, lithium, sodium, and potassium, calcium, strontium, and barium. And magnesium, manganese, and iron showed similar properties. Fast forward to 1869, when Russian chemist Dmitry Mendeleev took things to the next level by organizing all known elements based on their atomic structure and properties. This is how we now recognize Mendeleev as the father of the modern periodic table. So there you have it, a brief but fascinating history of the periodic table. Quantum mechanics is a significant part of our history, as it all began in the 1920s and 1930s. Scientists like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger laid the foundation for our understanding of quantum mechanics. They introduced us to the concept of wave-particle duality and Heisenberg's uncertainty principle, which paved the way for our current discussion. Fast forward to 1981, when physicist Richard Feynman gave a talk at Caltech about computers and their limitations. He introduced the idea that perhaps there were other ways to compute better than traditional computers. This led to the birth of the concept of quantum computing and the theory of quantum computation. Over time, many experimental breakthroughs occurred, such as Schur's algorithm in 1994, which showed that factoring numbers using a quantum computer could be done in polynomial time compared to traditional computers. This was a game changer in the development of quantum computing.
Quantum AI is rooted in the foundations of quantum computing, which can be traced back to the 1980s and 1990s. Physicists like Richard Feynman and David Deutsch laid the theoretical groundwork for this field. Fast forward to the 2000s, and physicist Peter Shor introduced two seminal algorithms, one for factoring numbers quickly and another for searching databases using amplitude amplification. Quantum AI combines this innovative computing power with artificial intelligence AI, leading to a hybrid approach that promises to revolutionize computational power and problem-solving efficiency compared to classical methods. For instance, consider an algorithm using both quantum neural networks and classical machine learning techniques to analyze satellite images more accurately than current methods. Overall, the fusion of quantum computing and AI in quantum AI is a thrilling area of research that holds tremendous potential for solving complex problems more efficiently than ever before.
Wave equations are fundamental to understanding various physical phenomena, ranging from sound and light to quantum mechanics. The history of wave equations is rich with contributions from many great scientists. Ancient civilizations studied waves, focusing on sound and water waves. The ancient Greeks also had a head start, with philosophers like Pythagoras exploring wave phenomena. Fast forward to Galileo, who discovered the relationship between string length and pitch in 1636, setting the stage for early research on wave equations. In 1834, Joseph Fourier revolutionized our understanding of wave equations by introducing the concept of Fourier series. These series represent any continuous function as a sum of sine or cosine terms and paved the way for the mathematical analysis of wave equations. The development of modern electrodynamics in the 19th century provided a foundation for understanding wave equations in this field. Maxwell's work on electromagnetism led to an impressive range of applications for wave equations, including telegraphy and radio communication. Today, wave equations continue to be essential in studying phenomena like electromagnetic radiation and quantum mechanics. Understanding these equations has opened up a world of scientific advancement and discovery. Let's take a brief look at some key milestones and contributions. Kicking off in ancient times, Mesopotamia and Egypt were bustling with mathematical activity from 3000 BCE to 600 CE. Early civilizations developed arithmetic, geometry, and algebraic techniques to solve real-world issues like taxation and construction. Moving forward about 1,000 years, the Indian subcontinent introduced a new era in mathematics from 400 to 1200 CE. Great mathematicians like Aryabhata and Brahmagupta made significant breakthroughs in trigonometry and algebra. From 500 to 1500 CE, China flourished with its own mathematics revolution. Mathematicians like Sun Fu discovered negative numbers, Zhu Shijing developed the first version of logarithms, and Zhang Juxiyun mastered the circle-square method. In Europe during the Renaissance 1450 to 1700, we saw a rebirth of interest in math with luminaries like Johannes Kepler and Isaac Newton making groundbreaking discoveries in astronomy and calculus. From ancient Babylonia to the rhind mathematical papyrus of ancient Egypt, algorithms have come a long way. Let's start with Babylonia, around 1800 BCE. The Babylonians were masters of mathematics and developed algorithms for arithmetic operations like addition, subtraction, multiplication, division, and finding square roots. These calculations were even used to predict eclipses. Moving on to ancient Egypt, around 1650 BCE. The Rhind mathematical papyrus is a treasure trove of ancient algorithms for arithmetic operations. It also includes practical applications in counting sand grains and measuring land for taxes. In conclusion, the development of algorithms is a testament to human creativity and problem-solving abilities. It demonstrates how mathematical thinking has evolved over time to solve complex issues that early civilizations faced.
This field has greatly influenced our modern-day society and involves the design, development, and application of electronic devices and systems. One of the foundations of electronic engineering is the discovery of electricity and magnetism. Key figures like Michael Faraday, James Clerk Maxwell, and Heinrich Hertz played crucial roles in this field. Faraday's work on electromagnetic induction in 1831 paved the way for our understanding of electric generators and motors. Maxwell's equations helped us comprehend the relationship between electricity and magnetism. Hertz's experiments with electromagnetic waves in 1887 were a turning point in our understanding of radio waves. The history of electronic engineering is an intricate tapestry woven by these pioneers and many more.
Let's explore the major milestones in this fundamental branch of physics. Ancient observations and discoveries. Magnetism. The ancient Greeks and Chinese recognized the magnetic properties of certain stones, lodestone, which were used as compasses. Electrification. The ancient Greeks also noticed that amber could attract small objects after being rubbed. Early scientific work. William Gilbert's influential book, De Magnete, explored magnetic phenomena and coined the term electricity in 1648. Benjamin Franklin's experiment with a key and a silk thread showed that lightning was a form of electricity. Michael Faraday's work on electromagnetic induction laid the foundation for electric generators and motors. Maxwell's theory of electromagnetism. James Clerk Maxwell unified electricity, magnetism, and light in his groundbreaking electromagnetism theory. His equations describe how electric and magnetic fields interact with each other and matter. And there you have it. A brief overview of the history of electromagnetism, covering key discoveries and figures in this fascinating field.